Hello, I'm Pam Hoffman, Everyday Spacer.
I'm Jeff Miller, 2049 Outfitters.
At Everyday Spacer, we show regular folks how to personally and directly participate in space exploration, science, and astronomy. We're here on Friday nights at 9 p.m. Pacific Time, 12 midnight Eastern Time, and let's pick one, 12 noon on Saturday in Hong Kong. We're broadcasting live from Thousand Oaks, California.
Tonight, we're doing a crunchy topic because you guys like those, and I like doing them.
We like them too.
Astronomical spectroscopy. So we'll be back in 8.3 seconds. This is going to be hard for me to say. Astronomical spectroscopy.
Spectroscopy.
It is the study of astronomy using the techniques of spectroscopy. Darn it. I was saying it fine earlier.
Spectroscopy.
To measure the spectrum of electromagnetic radiation, including visible light, ultraviolet, X-ray, infrared, radio waves.
Infrared. Let's do this. Hi, Scott. Yeah,
hi, Scott.
Crunchy topic.
Thanks for the distraction.
Thanks for joining us. Hey, Janie, happy Friday to you as well. All right, try again.
Including visible light, ultraviolet, X-rays, infrared. Infrared is actually, no, I guess that's used in a different way. And radio waves that radiate from stars and other celestial objects. A stellar spectrum can reveal many properties of stars. Man, I read that as propellants. Doesn't make any sense to me either.
Hey, Dawn, welcome. Thanks for joining us. Love that EM spectrum. Yes.
Yep. Such as their chemical composition, temperature, density, mass, distance, and luminosity. And some other things too. Spectroscopy can show the velocity of motion toward or away from the observer by measuring the Doppler shift.
Yep.
Spectroscopy is also used to study the physical properties of many other types of celestial objects, such as planets, nebulae, galaxies, and active nuclei, galactic nuclei.
And my friend Donald in New Hampshire asked a question. I wonder if they can do it for meteorites. And I thought, well, that might be pretty hard because there's no way to predict them, and they go very fast, and it's just little bits. It's dust particles and stuff that come through the atmosphere, right?
Yeah, they have been making inroads, and I'll talk about that a little bit, on reflective spectroscopy.
Right. You were telling me about that.
Yeah, which we'll do a little bit more. And also then, if there's any dust given off by the meteor as it's going, or if you get a really good shot using something that can break something into a spectrum of a meteorite coming through the atmosphere, that'd work too. But man, you'd have to get just right.
I guess you'd have to have one focused on the sky at all times to really
you'd have
capture something.
Yeah.
So there you go, Donald.
Yeah.
Maybe he's watching, but maybe he'll catch the replay as well. All right, I'm going to start here because you may recall, if you were here a couple of weeks ago, that we talked about this, and this was kind of the inspiration for doing this crunchy topic show. I saw Dawn had a comment.
Oh, for meteors, there is color as it burns in the atmosphere.
I've seen that chart before. Yeah, and you can tell what the composition is because of the color of it as it burns in the.
Right.
Well, they say it doesn't actually burn, but what else are you going to call that? A blaze? I mean, that's burning, isn't it?
No, what it is it's getting hot enough to fluoresce out the color, kind of like an incandescent bulb. Okay. And different things produce different colors of light, different chemicals.
Oh, okay. Well, anyway, so just in general, this is the study of astronomy using spectroscopy to measure the spectrum of electromagnetic radiation. And it's just astonishing to me. And I keep hearing about things all the time. Like even Jeff has told me some new stuff. I was like, dang, what you can tell from a rainbow. I mean, really, it's a rainbow. And we'll see more about that. In fact, this whole page, this Wikipedia page, has some really good images. Like you may recall this one too. I really love this, how it shows, what can come into our atmosphere and what cannot, what gets stopped, that kind of
Which,
thing.
of course, tells you why the visible spectrum is where it is, because that's
Yeah.
what our eyes were designed to see, is
Yes.
stuff that actually gets through the atmosphere.
What we evolved on this planet. And there's the general, you've got the continuous at the top, and you've got an emission line type, and then an absorption line type here. And Jeff will talk about more of that. But I'm just going to go quick because I found this really good site here too. I just loved the explanation. Astronomical images carry a lot of scientific information hidden within the beautiful colors. But even that's only part of the story. A great deal of knowledge comes from analyzing the light as broken down into its spectrum. Just beautiful site, beautiful information. Really, really like this a whole lot. I got a couple more here, and then I'm going to turn it over to Jeff. And then I'm going to come back and talk about, can you do this? And it's kind of an interesting answer. So there was an article on a site, and I can't even get to it now, but it looked terrible. I decided to come over here. And apparently they think that if we find life on another planet, it's because of its rainbow. Isn't that something? All right. And this was the European Space Agency, ESO. Even now, it still has some of the stuff from the article. But yeah, they talk about it as an analysis of sunlight by Fraunhofer and Kirchhoff. Did you find that in what you learned? Okay. But of course, we talked about Father Secchi as well. And he, these guys, he wasn't the first one to use it, but he was one of the first people to apply it to different stars and cataloged about 4,000 of them.
Right.
So this is a pretty interesting article on the European Space Agency. And I really wanted to show you this too, because as they say, it's they say, one of the things said it was a fingerprint of the sun. In fact, they've taken this really long image and put it into this, a little bit different site, and they call it like the barcode of the sun. A very long spectrum was chopped into small chunks and then displayed one on top of another. I think that's such a cool sight. So if you ever see that, you're like, oh, that's the sun. Mm-hmm. That's what the sun looks like broken down into. And I really, really love this image here. In fact, I went and got it a little bit easier to see. You've got this continuous spectrum, and they show a simple telescope. Makes sense. Then they talk about an emission spectrum and an absorption spectrum. And those are definitely different. And I'm not sure about why it comes through this way versus this way. But I think maybe Jeff will have more about that. But yeah, this whole article was really a great, foundational piece. So yeah, a little bit more different images. And any of these are going to be coming through a slit, sometimes even a little tiny, like a pinhole camera, basically through this, this slit that helps you to see things. We got another comment. Go ahead with, hey, Daniel, welcome. Nice to see you.
Yeah, I like that star code / barcode. Yeah.
Star code. I love that. Okay. So yeah, most spectrographs select the light to be, my eyes are going funny tonight. Select the light to be split using a slit, which can be long or very short, so different sizes, or even just a small hole. When that light is sent to the spectrograph, which is not shown here, produces a spectrum of that slit. I'm going to let Jeff talk about more about all this stuff, but I did find, I think, one more, from Cambridge, this 978-1-107, and it's weird because it says introduction to, unfortunately, you see how it says it's only a 10-page PDF here, because they reference quite a lot more, hundreds of pages, in fact, when you look at the
table of contents.
Yeah, the table of contents. So I don't know if you looked at that at all, Jeff, but
I did not look at this one.
Yeah, there's
down to the table of contents.
Yeah, this is some more information though, but IMMO Appenzeller, Center for Astronomy, University of Heidelberg. So I just want to make sure that was there for a minute. Cambridge University Press, and a whole bunch of other information, just like the inside of a book when it's published, the ISBN number and stuff. But here they have lots and lots and lots of. So somewhere out there, is the rest of this article about.
Yeah,
Or, well, it's a book, really, I suppose.
this is probably just a teaser like Amazon does, where they give you a few pages to let you know
yeah,
what
could be.
what you could buy from them or something.
Yeah, but they reference, like, look at this, 225, and it goes on. 251 total. So, well, that's just the beginning of the index, sorry. But yeah, there's a preface here, and that's really it.
Mm-hmm.
And then the next thing I'm going to hold off on for now, because I will talk about that a little bit later on. Are you ready for yours?
Sure.
Okay, so I really wanted Jeff to do this part.
Yep.
Because he kind of did more of the research. I just found some real basic information and good places to start.
Yeah. Okay, so I'm going to be hopping around a bunch of different pages because some of them explain different parts of it better than others, and some of them have different images that I really like. So spectra, everyone knows from the rainbow, and this has a really good. I just like this image. I like the colors in it.
Yeah.
But in here, for anyone who didn't know, shorter wavelengths are in the blue and violet. Longer wavelengths.
So is that ultraviolet?
Yeah. Well, it starts at gamma ray and goes to.
Well,
radio.
But it's like that violet, ultraviolet side, yeah.
Yeah. So this is, and this is what everyone is talking about with spectrum. It's just the frequency of the light. And
I make that a little bigger for everybody.
Oh.
Yeah. Oh, and Dawn's got a comment here. I think you have one article out of conference where more papers were presented. All right, thanks, Dawn. And then Daniel comes in with, in ancient Greek, the word root, gram, refers to something written or drawn, while graph refers to an instrument for writing, recording, or drawing. So a spectrograph makes spectrograms.
Yes. Yes. Actually.
Nice. I like it. Thanks, Daniel.
Now, yeah, as Pam mentioned, and this is a slightly bigger image, and again, I like the colors on it.
Yep.
The difference between an emission line and an absorption line, and they'll get into it later on, but
this is a NASA site. Cool.
Right. Yeah. Black body produces an almost even set of colors depending on how hot it is.
So black body, let's give a general
It just
idea.
radiates out.
Okay.
Like
let's say you took a phaser and heated up a rock. After it cools down a little bit, that's a black body. It'll emit light that way.
Right. Yeah.
Okay.
Anything
got
hot, like an incandescent bulb.
Okay.
Anything hot produces light, and the color of that light is based on how hot it is, and that's how you get the colors of the stars.
Okay.
Like blue stars are really hot.
Yep.
Red stars are cooler.
Yes.
So that's how you do it. Now, emission lines are when an element the electrons in an element are excited, then they drop down and they release a photon. And different elements have different energy states for their electrons. So they drop down at very specific, quantifiable distances, which quanta,
Yeah.
that was part of the start of all of that, was seeing this nonsense. So an element will give out lines at very specific spots because there's only so many places that the electrons can end up to drop down.
Yeah, in fact, I think there's like tubes of, say, neon or argon or whatever,
right, yeah,
so that you could get a spectrum from it. And they probably calibrate. I haven't read anything about that, but they probably calibrate their equipment using that kind of a thing. And I think they have to heat it up, right?
Right. Now, an absorption line is something, the element isn't emitting the light, it's between you and the light, and the electrons absorb some of the light and get excited. Now, as we learned earlier, the electrons can only go into certain spots. Mm-hmm. So only certain frequencies will excite those electrons, which is why the emission and the absorption spectra are essentially identical mirror images of each other. Basically, the areas where it emits light are the same areas where it absorbs light. So every single element will have essentially the same emission and absorption. It's just that emission it will produce light at those frequencies, and absorption, it will absorb light at those frequencies.
Okay.
Um,
It's a little bit hard to understand the absorption part, so maybe we think about a good analogy for
Um,
that. Because
there,
emission,
there,
you
there are
can
some,
kind of see.
right,
You heat up neon in a bulb, in a tube of
right,
of gas, and you'll get those lines, right? The emission lines.
right, yeah.
But an absorption is that like, let's say it's cooled off and you put it in between like another bulb with helium, that kind of thing.
Well,
And
basically, no. If
you'll
you put
see
it
the
between,
dark for the neon.
if you put it between you and the sun, let's say just as
Yeah.
a light source,
Right.
the light coming through it, some of those photons will be absorbed by the helium,
Okay.
and by absorbed, I mean it'll hit an electron and jump the electron to a higher energy state.
Because they'll depict them in like science books as having shells, and then
Right. They're not. It's just energy
It's not.
states.
Yeah.
It's just energy. We talked about that in an earlier
Yeah.
one. But so that's what the absorption one is. Those
Okay.
are the frequencies that it can absorb the photons. Because the electron can only go from one state to a set of different states, and that's
Right. Oops. Let me
we'll
go
see
back.
that.
You got a picture, right?
Yeah. Well,
Okay.
here, let's see. I don't think there's anything else on here. This is the NASA site. It's a really good. What is it?
Yeah.
It doesn't get into any kind of detail. Like it doesn't tell you how absorption lines are actually made. Just
Well, it's like
these
reading
are
a kid's
absorption.
book to learn
Yeah.
anything new because you don't know anything
Mhm.
about it. I think kids' books are great places to start.
Right. And this is a good place to start for someone who doesn't.
Awesome.
And they do mention hydrogen will not look like helium. But
Yeah.
this is the
Mm.
Webb Space Telescope.org.
Nice.
And what is spectroscopy?
As in James Webb, right?
Yeah,
James
as in the
Webb.
James
Okay.
Webb.
Yeah.
Yeah. Now, here is the sun. Assuming that there wasn't anything blocking it or absorbing anything,
Mm-hmm.
this is what the sun would look like to us. And this is the frequency range.
It seemed
of
like
the
it was
sun.
a particular instrument too, like just looking at it through a prism
Right.
or a telescope, or
Yeah. And
because remember that fingerprint of the
Mhm.
star code,
Right,
like
yeah.
Daniel said.
yeah. And this is basically low resolution. If you get high enough resolution, you will see the lines in it.
I see.
But this
Okay.
is, compared to the sun, this is a fluorescent light bulb.
Fluorescent. Okay.
And again, there's chemicals in the light bulb
Mm-hmm.
that emit light at certain frequencies.
Mm-hmm.
And to get white light, they put multiple chemicals in it to, like, you notice it doesn't give you full spectrum,
No.
but it gives you some of a little bit of everything.
Ah.
And so that's how it averages out to white
Right.
or white-ish,
Right.
as opposed to
Yes.
the sun, which has all of the frequencies generated.
Yeah, because when you mix like paints together, it comes out black. When you mix light together, RGB, for example, it comes out white.
Right. Yeah. And so what can it tell us? Again, it can tell us the temperature, speed of rotation, because there's actually a difference, Doppler shift between this side of the sun and this side of the sun.
Right. And I think everybody knows what Doppler shift is, but if you don't, in sound, it's that train that's oncoming, and as it goes past, it changes. It's the sound is compressed in front of the train as it approaches you,
Yep.
and it gets stretched out.
Okay.
I have a good art.
Here.
Yep.
Basically, as
Same
it comes,
idea.
Yeah, as it goes toward you, they're compressed.
Yeah.
As it goes away from you, they're stretched out.
Yeah, I do have a Doppler page.
Yeah.
Let me make
But
sure
this was just handy, so I did it. Now this, if you notice, there are lots of these things in here. In fact, there's a next here that will just take you to there. But here's part 2.
That looks like a wonderful article.
It is this Webb space, and it shows you, okay, electromagnetic spectrum, visible light is right here.
Oh, that makes perfect sense too for
Yep.
for Webb, because that's what they've been focused on, is a very specific
That infrared. They've been focused
Right.
over here.
which we can't really see, because you remember that
Right.
atmospheric, it's blind. We're blind
Right,
to
yeah.
them here.
Yeah.
Even with the right kind of equipment.
Right. So this is a mechanical wave. This is an electromagnetic wave.
It looks more three-dimensional.
Electric field goes this way. magnetic field.
So is that this way
is-
versus this way?
Yeah.
Okay.
Yeah.
Oh, we got a comment. Hey, Cliff. Aw, sorry to hear
Cliff.
that, man. He's still having issues with his internet.
Yeah.
Well, thank you for being here. We really appreciate it and your effort for joining us.
Yeah. And if you click on view description, it'll actually give you more information on that. So it's really good. You can drill down into.
Can you grab that and put it in the chat for people?
Oh, sure.
I think that's really worthwhile looking at.
I was going to grab a bunch of these, but yeah.
It looks very clear. It looks very.
This is a really good way of learning it.
Yeah.
And I have some other ones that, go into a little bit more depth. But
excellent. That should be a clickable link in the chat now.
Yep. Okay. This is how do you get a spectrum? Sunlight through a prism.
Yep.
Now they do it a little bit more robust than that, but again, here is the higher energy, shorter wavelength, lower energy, longer wavelength.
So it even looks like it.
Right.
It's like packed up a lot of waves in a short space.
Yeah.
For the higher end.
Yeah.
Okay, cool.
And here they're introducing the concept of electrons, and these are the types of spectra that you can get. Absorption, which is it goes through something. Emission, it creates it. Transmission, light can pass through it. Reflection, it reflects off. Refraction. So this is the behaviors of light. Now you can get spectra off of all of these.
No kidding. Okay.
However,
didn't realize that.
The transmission and refraction will give you essentially absorption. Reflection will also give you absorption. The only one that gives you emission is if you heat up the thing and it's radiating.
Oh, and Cliff says, so is the missus just kidding you? Okay. I don't know what that means.
Okay.
I think he means maybe on her phone, because sometimes that's how he joins us.
Yeah. So part 3, we're going to start digging in. The next part shows some real science going on
here.
It
keeps going there. I notice there's more parts now that is. Okay, cool.
You get to about part 6 or 7. I forget which one. And then it starts going to talk about the James Webb itself. So it's kind of like they stick each topic. Yeah, they stick each topic on the first part of it. Then I think they copy paste the stuff on the James Webb onto the back end of whatever topic they were doing. Because of course they're promoting the James Webb Space Telescope.
Well, that makes sense.
Yeah.
It's the website. Okay. All right. Back to your picture.
Yep.
All righty. There we go.
So this is showing you, this is hydrogen, and this is the energy emitted by probably the sun. Just looking at this curve, that's probably the sun. And if you notice, it's not 0 in the dark lines. It's just less.
Oh, interesting.
This is how much energy is coming in on each frequency, because we've got the equipment to basically measure the energy level of each frequency instead of just showing them onto a sheet of paper and marking them, which is what Secchi did. He projected onto a sheet of paper and just mark where the absorption lines were.
Okay.
But so
this gives me a sense of a 3-dimensionality to it.
Right. Yeah. This is
interesting. Is that okay? Lots to think about here.
Yeah. This is the sun, and if you notice, there are a bunch of dips, but these are the dips that are the signature of hydrogen.
Okay.
And types of spectra: continuous spectrum, emission, and this is like the image there, and absorption. Basically, the light goes through, and what comes through it is you get the absorption spectrum, but that light will excite some of the atoms, and it'll emit. Now, if it's between you and the sun, you won't see the emission spectrum because the light coming through will be enough that it washes out the emission. But if you're looking at it from the side, you're just seeing this. You're not seeing that. So that's how you
much
can see,
clearer.
Yeah.
Okay.
So if there's a nebula between you and the star that's lighting it up, well, if it's really close to the star, you won't see anything except the absorption spectrum. If it's far enough away, the star will be small enough that there's only going to be a spot like right there where you won't see
Okay.
the emission, but the rest of it might be far enough off of the arc to be visible.
Mm.
And
Boy, that is interesting.
And they give a good, okay, here's the colors, and this is also showing you the brightness, there, or the brightness dip.
Okay.
And this is the black body curve,
Mm-hmm.
and it's all based on how bright something is, or how hot something is.
Okay.
Continuous spectra, and again, blue star, hot star, has this curve here. Yellow star, similar to ours,
right,
has a curve here, right in the middle of the visible spectrum. Which, hey, either that's a really nice coincidence, very coincidental, or we developed to see what was most visible, which, hey.
Well, yeah, that makes sense that we would evolve that way.
Yeah. And a red star, which is far on this end of it, which you can't see it, but it produces the majority of its light in the infrared.
Mm-hmm. Yeah.
So absorption spectra, and here you can see it plainly here. Sodium, absorption, emission. You notice that exact nitrogen,
right,
hydrogen, oxygen. Hydrogen is the easiest one to see because it has so few and they're very distinct. But they're all there. And this is one of Secchi's things.
Cool.
And he'd mark these.
Now we know about him. Keep showing up.
Yeah. Yeah. And so he'd mark, where the colors are. And if you notice, some emissions, mostly absorption here.
Mm-hmm.
And this is Earth's atmosphere. Transmission spectrum. Again, this is what goes through the atmosphere.
Okay.
Water peaks here, here, and here. Carbon dioxide peaks here and here.
There's water again.
Yeah, and oxygen. So, that's, and here is a good chart of emission spectrum. And some of these look kind of fuzzy.
What's the title for this segment?
This
emission
is
spectra. Okay, sorry, I just didn't see it.
Yeah. And this is when you're looking at something, they set filters to look at specific wavelengths.
Okay.
And so
a lot of filters come into play with science.
Yeah. So they have filters that look for oxygen, filters that look for hydrogen, filters that look for nitrogens, filters that look for sulfur.
And they do look a little bit different, so you can see.
Yeah.
Do they tell you which Crab Nebula? Okay.
Yeah. And so this is, and then they essentially take things that hit that filter and assign them a color. Graphically, they assign it a color.
Okay.
And that's how you get the beautiful nebula photos. Is it's usually not the color that it actually is, but the colors, artificial colors, to show what elements you're seeing.
Yeah.
Reflectance spectra.
Yeah, that's a new one on me.
You can get spectrums from reflections. The trouble is that you get not only the element that's reflecting it. Oh, and reflectance spectra. We do that all the time.
Yes, we do.
You're getting a reflectance spectra off of this.
Yes.
It looks somewhat bluish.
Yeah.
At least in the monitor.
Right.
Looks purplish to me, but
it's purple.
But so
it looks purple.
Our eyes are spectrographs.
Yes.
That's
for visible light.
For visible light.
And just so you know, Cliff, I knew you meant your wife.
Yeah.
Cliff.
When you're using instruments, as you can see here,
whoops, let me
in
go
this
back.
thing.
Yes.
And this is what they're looking at, different planets and stuff, because they're learning on the Earth. They're pointing stuff at the Earth.
Makes sense.
To see stuff and figuring that then we can use it for other planets.
What is vegetation? What does it look like?
Water looks like this. Dry soil looks like this. Vegetation looks like this. Snow looks like this.
So it's a transferable idea.
Right, except that the shape of the matter matters too.
Okay.
If it's smooth versus rough, it'll be different. So there's a little bit. They haven't really gotten this, as far as I've seen. They haven't really gotten this as a science. It's still somewhat of an art.
Okay.
Those who are really good at it can spot them. You know, but are they just spotting what they want to see or not? You know, we have to do a lot more testing.
This kind of actually goes back to that thing. If we find life on other planets, it'll be because of the spectrum.
And the spectrum.
Isn't that interesting?
But this is the kind of spectrum that they're getting off of most planets. Now they get some where the planet starts to occlude the sun, occult the sun.
Right.
And you get, just as it's starting, you get the spectra of the atmosphere.
Right. So we know the star. And then, of course, when something comes past it, look at that, it changed because of the atmosphere of the other body that's...
Right. And you'd get an absorption spectra off of that.
Right.
You know, the reflection spectra is an absorption spectra. It's just that it has to bounce off, which the bouncing off also changes things. So that's why it's messy. So
you kind of get two out of the one as it comes across, right?
Well, you don't get the absorption from it occluding the sun.
Oh, okay.
It has to be far enough away that you can actually see the planet.
So the star hits the other body and then it comes back to us.
Yeah.
I see. Okay.
Yeah. And we've just started to get instruments that are sensitive enough to see planets.
Okay.
Not well.
Interesting.
And, you know, but hey, we're getting...
Well, that'll get better and better as everything else.
Yeah, then they talk about naked eye spectroscopy. That's exactly what you're doing right here.
Yeah. I like the way they term that because, you know...
Yeah.
Yes, you can do.
Yeah.
The science.
Yeah.
You do it all the time.
And now, here it gets into...
so neat.
How absorption and emission...
Wait a minute. Let me go there.
This is how absorption...
You were talking about it and I didn't have it. I'm so sorry.
Yeah. Pay attention. But, light absorption by hydrogen. And this talks about how I talked about the excitement of the electrons, different frequencies. These are the energy states that the electron can live in. And so if violet comes, it jumps it all the way up to here. If darker purple comes, it jumps it up to here. Blue light jumps it up to here. Red light jumps it up to there. But it can't, the electron cannot be in any states that are in between.
Right.
They
it's very
just can't
quantum.
do it. Yeah.
It's very quantum.
In fact, that's where quantum started.
Yeah.
But so this is an absorption spectrum here because it's absorbing those. Now, once it releases those, it can only go from here to here, from here to here. So again, it's just as quantum coming back down.
Now, is that the reflection?
No, this is just emission. No. This is emission.
Oh, okay. Well,
the electron had gotten excited up to here.
Yeah.
And then it
fell back down into.
Fell back down, and which is why, like, if you're looking through the cloud directly at the star, you don't really see it because it's absorbing and it's transmitting, you know, but it won't transmit as much. So it'll look darker because it'll transmit, you know, it'll transmit this stuff in all directions. So you're only going to get the parts of this that are coming toward you.
Yeah.
So it'll look darker. You know, so like the net effect of this going through the sun is that this will absorb more than it'll transmit back out toward you. Which is why the net effect is it'll look darker on those wave bands.
Okay.
You know, and there are different, I showed you before that different atoms and molecules have their own absorption lines. One of the neat things is that helium was actually discovered by looking at the sun. they found absorption lines that didn't match anything else that we knew. And so this must be a new element. And so they call it helium. For the Greek for the sun is helios. So it's helium. And it wasn't until about a decade later that they actually found helium on Earth. And then noticed that, they
Also
heated it
because of the spectrum.
Well, they found it, and then, well, what kind of spectra does this produce? Because it's a new element. Well, they heated it up. It produced the lines exactly where helium was absorbing it in the sun. So, there we go.
It's kind of beautiful because it's a little bit like math. I mean, 1 + 1 is 2. And if it looks like this, it is this.
Yeah.
That's all there is to it.
They also thought that they found another unknown element by looking at the corona, but it turned out to just be an ion of iron.
Okay.
It had lost some of its electrons, and they were in a kind of excited state, so it wasn't quite, didn't quite match iron. So they thought it was something new. And then
it kind of was.
And then in a lab, they of course, in the labs in the early days, they were doing emission spectras of just about anything they found. So they found this, they made these ions, did the emission spectra, and go, oh, that's what it is. It's just iron missing some electrons. So that's
got it. You going back? Hang on.
Yeah, hang on.
Let me go there too.
Yep.
All right.
Okay. Beyond temperature and composition. And
I thought this was neat.
Yeah.
Go back to that word. Density. You're going kind of fast, so.
Yeah. Well, I wanted to get to the image because the image looks neat.
Yes.
So density. You can tell the density of something because like a blue giant, which is very low density, if you notice, all of these lines are very sharp. But a white dwarf with it has high density. See how much bigger and fuzzier these lines are? And the reason for that is the pressure and heat in this high density white dwarf affects the electron shells. It's close enough to other atoms that the electron shells are shifted. Not all of them, but there's enough of a spread to make these lines wider and fuzzier.
You want me to show it again?
Yeah. Yeah, there's enough of a shift to, make the lines wider and fuzzier. So, and also some of the lines are moved relative to the others just because those energy states are slightly different. So that's just, so if it looks fuzzy, it's a highly dense, and they're using this to check they used this to check the compositions of some things. And even still now, what's the difference between a blue giant and a white dwarf? Well, one's fuzzy, the other one's not. They could both, if the blue giant's really far away, it could be as bright as a white dwarf. But if the lines are sharp, it's a blue giant. If they're fuzzy, it's a white dwarf.
It continues to fascinate me how much we can know from this rainbow thing that we have called a spectroscope. Spectrograph, I guess, right?
Yep. And
motion. Yeah.
Everyone knows this one. I mean, we've talked about this in so many different ways, but blue shift, red shift, basically, as it's moving toward you, the sine wave compresses essentially. As it's moving away from you, it kind of stretches out.
Yeah, it's still fascinating to me though that you can tell that it is moving away from you or towards you again from this image. This image of the spectrum.
And this redshift is what proved that the universe is expanding. Because either that or it was highly coincidental that most of the stars were moving away from us. Otherwise you had to explain why our planet has such BO that all of the other stars are moving away from us. So cosmological redshifts, this just gets into that. You can view description, expand the image. We've talked about this sort of thing before, but if you want more,
wow,
this is This is there.
Really fabulous
Yeah.
pages on this website.
Invisible spectroscopy.
Now we're getting into the...
Yes. Because atoms don't just produce spectrum in the visible range. That's where we can, those are the ones that we can see.
Right.
Because there are other, in fact, you saw the hydrogen example there where it had the electron shells, and I'm not going to go back to it because I don't remember which one it was, but one of the shells that it showed, there was an inner shell that it didn't show any lines for. It's because those jumps are either so high that it's in the far ultraviolet, or just from one shell to the next one, which is in the infrared. So we don't really see those. So even though it's possible for it to do that, we don't see those. So
well, the James Webb can see it, right?
Well, the James Webb can see the infrared ones.
Right.
It can't see the ultraviolet.
Infrared,
ones.
yeah, right.
Yeah. But, since...
Are we going back?
No. Oh, yeah, to this.
Okay, yeah. Here we go.
No, this is just talking about the James Webb, how the James Webb does it.
Well, that's cool. That's good stuff.
Yeah. And James Webb has micro shutters. Sorry, guys, I can't make this any bigger. I tried clicking on it. Here. Get the full micro shutters infographic. Let's see.
That might be good. It's smaller.
Zoom image.
Oh, well, that happens so much.
Okay. The zoom image. Oh, here, I can plus it. Okay. Okay, here.
How about the big X?
I can't.
Up there?
Can I make this? No, I can't make this.
No, there we
go.
There we go. Oh, it's still.
Yeah. Okay. So.
To explain what the micro shutters are, because now I want to know. Oh wow. Those are micro.
Yeah. And they're just like LED type things, LCD type things where they just close and open. Magnets selectively open tiny doors all across the array, allowing the instruments to capture light from up
well,
to
if it's LCD, it's probably
right
arranging them, and I'll kind of. So if they're like this and you can't really see anything, they might go like this, and then you can.
Yeah.
Okay.
Right, but it's got so many different gates that it can look at 100 different objects at the same time, because it just opens the gates for those objects.
Okay.
As long as they're far enough apart, they don't interfere with each other.
Wow.
So you get this one open and this one open, and you're looking at two different objects.
I'm glad they spent that time to make that work properly.
And then each one, they split the light.
Wow.
So.
Okay.
So that's that infographic. So that's just, and I
Sweet.
think, yeah. And these are the various instruments that they have and what they can look at. Now the infrared is not something that we normally use for spectroscopy, except that as things get farther away from us, they're moving away from us farther and farther. So like the hydrogen lines will go from here to over here if it's far enough away from us. So that's how we can tell the chemical composition.
Not only moving away, but how fast, I bet, right?
Right, yeah.
Okay.
So
cool. Because the farther over, the faster it's going.
But it lets us see what stars that are far away, thus older, are made of. And they've shown that it's mainly hydrogen and helium at the various farthest stars. Again, one more piece of evidence for the fact that the elements come from stars going nova.
Yeah.
So oldest stars don't have many of the heavy elements.
No. Many,
if any. Newer stars do. Oh, and Daniel has something.
Oh, just noticed. Okay. 80% of the universe is dark matter / dark energy that we don't understand. Yes. 20%, I think it's more like 95. The 20% that obeys gravity, electromagnetism, and strong and weak nuclear forces we have figured out is still pretty cool.
Well, and Daniel, that's a maybe. because there are some theories that do explain what we're seeing in the expansion
Mm.
of the universe without using dark matter.
Mm.
Now they have some issues, but if we spent as much time messing with them as we do the current theories, we might work out some of those issues. Don't know. Still up in the air. Still
Who got the funding? That's
Yeah.
what gets worked on.
Yeah. So currently dark matter, and dark matter is simply, it doesn't even necessarily have to be matter. It's something that produces gravitational effects.
Yeah.
Because we
Yeah,
do
they've talked
see,
about virtual matter. Which...
so yeah, the biggest evidence for dark matter is gravitational lensing, where there isn't anything that we can see.
Mm.
So
yeah, and when I talked about virtual, it's something that's very small and has almost no mass, but it moves very quickly,
right,
like a neutrino. It
Right.
may have actual so-called virtual mass because of its
Right.
swift motion,
right,
even though it has very little actual mass.
right. So the current theory of dark matter is it has a gravitational effect, but isn't affected much by gravity itself. Because
Interesting.
to get the rotations of various galaxies using dark matter as the reason, is that the dark matter has to be distributed evenly in the galaxy, not clumped in the center where mass is. Because with a galaxy, most mass is clumped in the center, with it getting
apparent.
Yeah.
Though it appears to be.
Right.
But in fact, it is distributed more or less evenly. Daniel has another comment. It's also the rotational physics of galaxies.
Well, yeah, that's one of our evidences of, but they do have some explanations for the rotation that don't involve dark matter. Again,
I haven't read that stuff.
How robust are those?
That, but okay.
We don't know.
Yeah.
So
what a great time to be alive, huh?
Dark matter is simply like the blank spots on the old maps. We just don't know what that is, what's causing it.
Yeah, I don't like the name. It's an anomaly. It's a mass anomaly to me.
Yeah, it's just, I guess they don't want to call it the I don't know.
Here be dragons.
Yeah, here be dragons. Yeah.
Works for me.
Yeah.
All right, you going back to the
yeah, but we're pretty much done with this site. I mean, it does talk. There are more things on
back?
here.
Am I going back?
Let's go back.
Yes. That's what okay, there we go.
If you notice, there are still 22 more pages, and it's more about various other things. It's not about
so really crunchy stuff. Yay.
Yeah. So you can, there's definitely more to see there.
Yeah.
So
and you put that link in the chat. So good.
Yeah. And here's the wiki that Pam showed. Now here is another way of doing it without using a prism.
Right. Diffraction grading.
And
you may have actually held some of that. It's sort of a see-through thing, but it kind of looks like rainbows.
A CD or DVD.
Oh, a CD or DVD has okay.
Yeah, it makes rainbows based on the light hitting it at.
But I'm talking about like in a science class. If you took a science class, you may have actually handled some. I think we have some around here.
Yeah.
I got from somewhere.
Yeah. But
good stuff.
So, again, this is an element, and these are various. They gave names to the lines.
Oh.
And so oxygen has these lines, and this one, and and these, and I don't know why they bothered to do that, but they did.
What's at the top of that column? What does it say?
It's three columns. Just they made it so that it's easy to.
Designation element wavelength.
Yeah.
Okay.
Yeah.
Well, we like to name things.
Yeah. Black body radiation at different temperatures. If you notice peaks, the blue peaks high in the blue. Of course, the lower temperatures produce lower peaks because less energy in lower temperatures. And red is here. It's a much flatter curve. So this is black body. This is what a star looks like. This is classical theory
Oh, so theoretical.
Yeah.
There's always loss in any system.
Yeah. So it gives a kind of overview about what the spectrum is, and then they go into math. And binary stars, how you can tell by the redshift of the two different stars. So lots of good stuff in the wiki too.
Yeah, still fascinating what we can learn from a spectrum.
And this is talking about the uses of the spectrum more rather than what is the spectrum, which is what the James Webb one was
so
mostly
for lots
about.
of things, did you see meteors like for a meteor shower?
Asteroids,
planets, asteroids, comets.
Yeah.
Of course, stars. They talked about nebulae, right? Galaxies.
Yep. Yeah.
Okay.
And obtaining this is csiro.au. So Australia Telescope National Facility, Cliff.
Cool.
So how does the spectrograph work? Slit prism makes, shines light on stuff. This is where, hey, this is what, this is a fraction grading too, a CD or DVD.
And I think most of us have handled those.
Right, yeah.
And that's how it stores the information from.
Yeah. And this is how most devices work. They have a slit here. They have a mirror here that takes this arc of light and makes it a steady beam of light. And then once it's steady and you don't have any spread from the slit, then it uses this to give, to split the light into its spectrum. And
okay. Well, that's very interesting because of the thing I'll show you next. But yeah, cool.
And this is shows a galaxy redshift, I think. But so this is, again, they've got some more stuff here. They've got spectral classes of stars, astronomical spectra. They've got a lot of stuff, good stuff on here. I think I'll share that as well because that's
awesome. Yeah, it looks terrific.
Yeah. And
thank you, Australia.
Yep. And then I've got a couple more things.
So Jeff added that. It should be a clickable link in the chat for you.
Yep. Now, this is a paper from Caltech. I'll let you read this on your own. It's
is it very crunchy?
Yes, it is.
It's very crunchy. Okay, is it all there?
76 pages, 84. Yeah, it's all here.
Oh, good.
So,
yay!
If you really want to get into it, here it is.
Oh, gave me an error.
I was might have been too long for Facebook, but
showed up here. That's weird.
Oh no, it's only for the everyday spacer. Maybe it just glitched. Okay, and then one more, tools of cosmology. This has some good history on it, so I'm going to.
Ooh, that's a neat site.
Yes. So I'm going to shoot you that one too. Then
we could probably find all kinds of stuff in there.
Oh yeah.
For various episodes in the future.
Yeah. Yeah.
I don't remember seeing that before.
Naked eye, first telescopes, or early reflectors, golden era reflectors or refractors.
There we go, spectroscopy.
And the birth of astrophysics. Because astronomy is looking at stuff. Astrophysics is essentially started with looking at these spectra.
Oh, that's not Secchi's, but
no, this is someone else.
The first guy that he noticed, I think, right?
Yeah, and Bunsen was another one that worked on it. In fact, these are called Fraunhofer lines.
No kidding.
But Bunsen of the Bunsen-Burner fame was also into it. And this is
there's Secchi's.
There's the Secchi's classifications of different types of stars, which led to the modern classification, which are more types of stars, but he classed things into 4 different types. So
4,000 stars that he gave those classifications.
Right. Yeah. So early,
That looks just terrific.
yeah. And they talk about anti-jump cannon here.
Yep.
Picturing the
Oh, and I
cosmos.
know that name very well.
Yep. The new technique appeared, and they get into a lot of the history of this. Is astronomers looking to photograph a solar eclipse in Spain in 1860.
Is Father Secchi there? I think he went to that one.
They don't.
He's in the picture. Can you
I
click
don't
on
know.
the picture?
Well,
yeah, look at that.
Hard to tell.
There's a lot of women there. Nobody knows that.
Yeah.
That's very cool, though.
Yeah.
Yeah, I can't tell if he's in there or not.
Yeah.
Well, thank you for checking.
Yep. And so new tools for astronomy. There's a lot of neat stuff in this website, so I'm glad I found it.
Yeah. Okay, Hal.
Yeah.
All right.
Yeah. So, so this is.
Yay. Cool new site.
Yep.
All right.
And so, okay, that's what I've got.
All right. So I'm going to go ahead and share this thing because what I decided I wanted to also learn was, can you do this too? Can I do this? Can you do this? Can anybody set this up and do that? And the answer is yes. However,
yes, but
I would like to caution you that you are going to definitely want to do some research and figure things out. And there is an investment. It's not quite as easy as going outside with your naked eye, with binoculars, a simple telescope, and looking at the sky. You're going to need some tools.
Which means, Cliff, if you decide to get into this, you're never going to see the sky
No,
again.
no, that's not quite so, because even a little bit of light will be helpful if you want to see.
But it's if he buys any more equipment, it's going to rain for the next decade.
Yeah. All right. So I'm going to go ahead and reference this AAVSO guide to getting started in spectroscopy. Now, let me tell you something here, because I did not feel, I actually made a copy of this and I went through with a pen, and I'm like, oh, this is really not for a beginner. First of all, you have all kinds of lingo, I say, is you definitely want to know more, I think, than this is going to give you. There's really no glossary for this. It's a wonderful article. Don't get me wrong. It is a wonderful article. It's only 24 pages long. I got through about half of it with my pen and marking everything up, and it's very crunchy. So if you love it, and you're gonna love it if you love it. So all right. So but they do talk about some good stuff, principles of, equipment of. But I really felt like after the introduction, which is here, I really felt like I was thrown into the deep end.
Well, and hopefully we'll get someone from AAVSO to explain this to us.
I actually contacted him again yesterday, and that's in process. So here is a drawing of what you had a nice picture of before, and I'm like, oh, now it's starting to make a little more sense, because this thing was just, oh my goodness, what the heck? It's very hard to understand from what I'm seeing here unless I know more.
Yep.
What this is, what it's about.
So this is more of a refractor type than a reflector type. The picture that I had was a reflector type.
Okay, so see, you just look at this. This is the first thing I found about how to, because a lot of those other things I found really didn't give me the how to do this, how to build something and go looking. It was more of a, what is it? And that's great. But I wanted to see, can you do this yourself? And you definitely want to know more. And when you get started, I would look at something different. And I've got a page for that too. But I think this is great for someone who's not a complete newbie. Let's put it that way. If you're a newbie, I don't think this is going to be very helpful.
And
I'm a newbie.
And it's not like you're going to be building that. You're going to be buying that. That's going to be an eyepiece.
Well, no, the one book talks about how you can build this. So
There you go.
I'll get to it in just a minute.
Yeah.
All right. So, it talks about the components. It's like, okay, great. I understand the slit part. I kind of understand this, but boy, I just started getting into this. I kind of understood this, but I just thought, oh my goodness, I really need like the link dispersion versus resolution. Okay. Of course, now that I've read this, I kind of do understand it better.
You need to spread it out,
Yes.
but then you need to bring it back down so that it's not fuzzy.
And that's why I thought the diagram you found was like, oh, now it's starting to make a little sense, because this one, it's almost just a...
Yeah, except that if you look at it, between the refractor versus reflector,
Yeah.
it's the exact same diagram.
Yeah.
It's just maybe as a reflector, it moves things around enough that you could see what was happening versus this one.
Yeah, I think you're right.
Whereas this one's actually easier for me to see.
Interesting. Okay. So yeah, sort of more like a blueprint versus looking at a house.
Yep.
Other equipment considerations. There's lots of great stuff in here. Guiding, flat fielding. What the heck is flat fielding? But if you get into it, you'll learn that stuff. Mm-hmm. Again, this is a great article.
Well, at least they discuss it in section 2.
Yes, right.
So
sure. But I'm seeing it here. Like, what does this mean? I'm putting question marks all over. What the heck is this?
Well, you can be happy that they'll over-explain it in section 2, and you may or may not understand it.
We'll see.
We'll see.
I did love the part where they said at AAVSO that you can submit your findings, what you see, and this is really good for people. And I know some of you out there already do this. They started right off the bat. Maybe it's in the introduction. I should have pointed out when they were there. That if you are already familiar with, particular for observers who already have some experience with imaging, and maybe that means just taking pictures. I'm not really sure. But they do, talk a little bit about CCDs and how you. And I kind of knew about this before, because CCDs are like an array of pixels, right? Mm-hmm. And some of them are bad. So one of the first things you want to do is get like a map of the bad spots. And I've heard about how to do that before, and they go into that a little bit here too. But yeah, this isn't a primer. This isn't a beginner's article. It's very, very good. I would just start somewhere else. And like I said, I have another page about that. So 24 pages long, not terrible for, the volume of information, but a little bit hard on what things mean. They do have some reference sites. This website goes to, and I have that up here too. It's unfortunately named ISIS, but it is a good piece of software that you can download and use. So we'll see that shortly. But yeah, I just really wanted something a little bit more basic, a little bit more starter for finding out how to make this darks. What the heck does darks mean? I really don't know. So I found this kind of difficult.
Well, darks are, and I've heard of this in other things. Darks are, you take a shot with the shutter closed and look for light spots, because those are bad pixels.
Okay, so that's how you find your pixel map, so that you don't read, bad spots as data.
Yep.
All right, so I got to about here with my note taking. So what I'm going to do is I'm going to go over here to this ISIS page and mention this this basic software, because I thought this was kind of neat. And there's lots of different things that they delve into here. But it looks like it's free to use. And
well, they've got the zip file right there.
Yeah, just download it. And I almost never want to say just download it, because of course, you want to make sure it's a safe site. I have a feeling that it is, especially because it was referenced in this AAVSO article. I definitely feel they're a trustworthy organization. Mm-hmm. And I feel that, of course you want to decide for yourself, but they do have, go ahead.
Well, they seem to have an instruction manual in French. That's nice.
Well, they might have another one.
Well, maybe right there in the here.
Here?
Yeah. If you notice,
procedure
for installing the database. Now that doesn't
Maybe the same
necessarily
thing.
say that it's
It's
how to
very
use it.
small, 2 megs.
Yeah.
Yeah, so I think if you feel comfortable about downloading from a site like this, check it out.
Oh, yeah, star analyzers. Yeah.
Yeah, I do love what they were saying that, in terms of you don't need a whole lot of light from the object you're trying to analyze.
Right.
You just need some because the lines are going to be in the same place no matter what.
Mm-hmm.
No matter what. So I'm going to go ahead and do this for these because, and I added a link to the in the description for these Amazon pages. If you're interested in it, I would start a little bit more like one of these books, and there's a whole bunch here, but I kind of split out into several of these, especially if they were like, if they sounded more like a starter book, somewhere you could start. But yeah, just a simple a search is going to find you a whole bunch of things. And I think things like this one, the Patrick Moore, in fact, that one's, I believe it's at the end of this here. I think that's going to be a really great place to start just from reading the description. And of course, I didn't have as much time to like go get the book and read it and tell you more for like a nice little a review. But it does mention here that you can, with some simple equipment, make yourself, a spectroscope, I guess it is, really, from things you can buy. So yeah, you can do this.
What gets me on this site is that they seem to have a range of prices for the Kindle version. Is that
I don't know.
New Kindle versions or the
I don't
old,
know.
or the old, or the
you want to get
ones?
a used Kindle book? I don't know. I was just strictly looking at, wait, can I find a beginner book on how to actually do this for myself? And I think the answer is yes. And I think this would be the place I would start, just reading the different descriptions for the books. And so there's the general list, and then I found a couple of other ones, grading spectroscopes and how to use them. Again, Patrick Moore. I think Patrick Moore has a great, although it's not by Patrick Moore, but I think that, it's a great place to find good information and probably good starter information too. How to use them, written for amateur astronomers.
Say no heavy mathematics or formulas.
Yep, right. And I think it's also for someone who's like, let's say you've been at it for a long time and you're kind of looking for some new things to do, new challenges. But honestly, I'd rather build a radio telescope before building one of these. After what I've learned, I think it'd be easier, honestly.
So we don't have a big enough backyard for a radio telescope.
Yeah, we do actually, but anyway, we don't have a place to put it. That would be the problem. But some other books, again, Patrick Moore is referenced in here, even though it's by someone else. But yeah, I think any of these would be.
I think Patrick Moore has become a brand.
Maybe. I think any of these would be a better place to start than that AAVSO article. Yeah, I saw the.
Janie says, thanks. I always enjoy learning with you guys and appreciate your research, translations, descriptions, and encouragement.
Well, thank you, Janie. We really appreciate
banter.
You being here.
Yes.
Banter, yes. So yeah, those are the
banter?
No, we don't banter. So those are the books I would kind of start with before, and then like going back to the AAVSO article and go, oh, now I know what this means. Because I have a feeling that's exactly what would happen for you. But yeah, starting there, I don't know. But yes, it is possible to do this yourself. And there's some free telescopes out there. I wonder if there's like free spectroscopes to do your research on. Makes me wonder.
Yeah. If they'd be in higher demand.
All right. So yeah, I don't know.
Yeah.
That's what I have for this. Did you have anything else for this?
No.
All right. So I guess we're going to head into, you want to do this next part?
Sure.
The stellar events this week?
I haven't looked at this before, so let's give it a go.
This should be fun.
So some stellar events this week, May 17th through May 24th. I'll probably do better this time than I did last week.
Maybe.
Well, it wouldn't be hard. May 17th, the moon is at apogee. It's 251,000 and something miles away. 251,432 miles away, to be as precise as we can get in counting in miles. If we counted in feet, we'd get more precise. and drive about 80% of the world absolutely nuts with that.
Let's see. Don says, can you give us the paper address, please?
The address of the paper.
Oh, yeah. I will. I'll grab it. But you know what? If I do, Jeff can't read this, so I'm going to let him finish.
Oh, go ahead.
Oh, okay.
Just go quickly grab it and then.
Yep. Yeah. Okay. Copy.
Sure.
See, this is why I don't want to do it.
There we go.
And it might, it's the PDF version, so hopefully that'll show up for you, Don. Let me know if it doesn't, and I'll help you out.
Yeah. Okay, May 18th, the moon is on the equator, and Venus and Uranus are in conjunction. Also, Jupiter and the sun are in conjunction. Might be hard to see Jupiter in that case.
It might be easy to see its atmosphere if it's...
Yeah.
Go ahead. Sorry.
I don't think Jupiter is going to be passing between us and the sun.
No, that's true. You're right.
It'd be a very bad day if that were to happen.
Yes, it would.
May 19th, the moon is at a descending node.
Yeah.
May 20th, Spica is 1.4 degrees south of the moon. Which, okay, that's 1.5 widths of your little finger.
Yeah.
May 23rd, full flower moon. Whatever. I mean, if they want a moon for grinding wheat, that's fine.
No, it's flower. Like roses.
Antares will be 0.4 degrees south of the moon, which it'll actually be an occultation in the southeastern North America. And Venus and Jupiter are in conjunction. May 24th is our Friday night show, where we might demonstrate a citizen science project. So we'll see which one we might do shortly. Find us Fridays at 9 p.m. Pacific time on the Everyday Spacer Facebook page and the Everyday Spacer YouTube channel.
What inspires you the most for the coming week? I've got one new site. Let me see. Do I actually have one new site?
Don't know.
Where is it?
I'll show it if you have it.
Oh, let's show this too, and then go ahead, because this is a little bit, yeah. Also, and they even have a audio of how it works.
This is how
the
Doppler
shift. Yeah, I had that page up. All right, so this is this is the thing I found. If you are a Buffy, as in Buffy the Vampire Slayer fan, there is a conference coming for you. It's called HellmouthCon 2024. Oh, and it's at Torrance High School in Torrance, California.
Which is where they filmed it.
That's where they filmed it, yes.
Where they filmed the outside scenes, yeah.
Yes, right.
But, oh, okay, Don.
Yeah, have a great week.
Thanks.
And you may recall this NASA Social one, and the Ensman Magazine's one, and so on and so forth. We've been at this for a long time, though, so I'm going to go ahead and cut that off, because I didn't really look for too many this week. And I know it's late for Dawn, so yeah, let's do that. Let's just cover the new ones. And
yep, okay.
So go ahead.
So if you or someone you know has done something interesting involving space exploration, science, or astronomy, we'd love to share our live. Join us again next Friday, May 24th. If we don't have a guest, we'll demonstrate Burst Chaser, another Zooniverse citizen science project.
I spelled it wrong there.
I actually said it right.
Yes, you did.
My eyes edited it, or my brain did.
Yes.
But
sorry.
Yeah.
So yeah, we are talking to a couple of people, though. We're hoping to have a guest.
Yep. Yeah.
We'll see what happens.
And we're hoping that Burst Chaser isn't done by next Friday too.
That can happen too.
It's happened.
Yes. All right. So let's do a shout out. Thank you, Dawn and Janie and Daniel and Cliff was here.
Yep.
And Scott was here.
Yep.
Did we miss anybody?
Nope.
We always very much appreciate your presence.
Yep. It
makes it so much more interesting for everybody. And you find things for us and you ask really good questions. So yes, definitely. Thank you so much.
I think maybe next week I'll bring the magic mirror.
Oh God.
You know,
What's
just
that?
the handle with the thing like this, and I see dawn. I see
I forgot about that.
romper room.
Okay.
Yeah.
I'll
Now
try
have
to
I
talk
told
him out of that.
T-Round here.
Anything else from you?
No, I might not even remember by next week.
Yeah,
So
good.
just
And we'll watch for your comments still. And I am so grateful you're here. Have a great week, folks. We'll see you later.
good night.
Bye-bye.